Dear colleague, dear students, welcome to this presentation on data management. It is divided into two parts. The first one is a review of data management. The second one will concern the validation check exercises and the use of software tools for exercises for data cleaning. Right. We will make this review, let's say, on the basis of let's say the book written by Chapman in 2005. He's a specialist in the field, okay, an expert in the field of data cleaning. So let's say his the reference I'm using here for this data management review. The data management principles are summarized by GBU Secretariat in a video based on the book of Chapman. So here it is. I encourage you to use that link so that we can understand the 12 principles of data management. Okay, here in this review, I can see that data are not free of error, and therefore data validation and correction are essential for data use. Yes, it is important to prevent errors in data entry as well as detecting and correcting them in data. In data cleaning process, the basic causes of the errors detected must be identified so that appropriate measures can be taken to improve data entry process in order to prevent the reoccurrence of those errors. The general framework for data cleaning is as follows. First, important to define and determine error types through our exercise on validation check. We'll go through this. Second, search and identify errors, and then correct the errors. We need also to document error instances and error types, and then modify data entry procedures to reduce future errors. Now, why data cleaning is needed? Let's say that we need to improve data quality to make them fit for use, determine the need of data cleaning. Data cleaning is achieved through errors detection, documentation, and correction. Let us say that errors in data are common and are to be expected. But there are two major causes of errors that are errors in spatial position, geocoding, and in species identification. It is important that errors are not just corrected, but corrections are also documented and changes traced. It is best to add correction. Therefore, it is best to add correction to the database and retain the original data in a separate field of document, in a separate field or document, so that whenever needed, you can refer to the original information. Generally, in the data cleaning process, you need to do this. You need to go back to the previous version in the process of data cleaning so as to check or to reconsider them when you find out that you have introduced other errors in data cleaning. But in data sets, where are the errors? Where do we find errors or what are the causes of errors? They reside in poor or erroneous geographic coordinates of legacy data. Legacy data are data from herbaria and museum. Because the first data to be collected for centuries are not georeferenced, but the places where they are collected were only text described. So post geolocating are done, and usually post geolocating is quite poor. There is a problem precision. Errors are also in taxonomic and nomenclatural information of observational and survey data because of absence of buffet of the specimen. Exactly, observational data are data that are collected, let's say, on the fields. And when collecting the data, we suppose that you have to do with this or that species. But we can be mistaken. And since we don't have a virtual specimen to submit to a taxonomist for clear identification, we can create bias in the species identification. Errors also are in opportunistically collection of data along roads, for instance, where access is quite easy. Along roads or around localities or along waterways. And this can result in large spatial bias because of, let's say, lack of completeness of data. So the data just cover parts of the country, of the region surveyed because of lack of access to other parts of the region. Now, the prevention of errors is preferable to their later correction, as said Chapman in 2005. Now, how can we prevent a spatial error? The issues to tackle in that respect are misidentification of species. This may place the record outside the expected range of taxon. So it is clear, if we don't have a good identification of the species, then we are treating a species that is quite different from what it should be. So you say that this species is found in that is found at that place, but it is not the species, it is another one. So it places the record outside the expected range of the right taxon. Issues to be tackled are errors in geocoding, latitude and longitude, for instance, and spatial bias in the collection of data. Where in some localities, for instance, when, let's say, the original data are not georeferenced with GPS, for instance, and it is text-based or text-described, please, post-geolocating can, let's say, let you attribute coordinates of a whole department instead of a place where you collect the data. You see? Further, a well-designed collection can contribute to gap filling in spatial error correction. So, for instance, when you display your records on, let's say, the map of your country, you can find out where the gaps are, and then design, let's say, field excursion to collect, let's say, data in the places where that are not covered by the previous collection, so that you can, let's say, you can fill the gap. Yes, tools exist to post-geolocate collection. That's geolocate, biogeomancer, and yes, my colleague in charge of teaching you georeferencing will come back to that, I'm sure. Now, how can we prevent taxonomic and nomenclatural errors? There are two main causes of error with this data. Okay? Then you have inaccurate identification or misidentification, which is error of taxonomy, and misspelling, which is error of nomenclature. The names form the major key for accessing information in primary species data, as pointed out by Chapman. If you don't have a right name, cannot access information on the target species. That is clear. There are tools to assist with identification of taxa. They include improved taxonomies, florae and fauna, automated and computer-based keys to taxa, and digital imaging of type and other specimen. For instance, you have catalog of life that holds global regional taxonomic name list. And on that sheet, you have actually more than 2 million of data on species. So it is important, okay, to use such list. It is a credible. You can also use the species searches of on GB sites, okay, that allow you for filtering for accepted names and synonyms. Now, let us come to the concept of data fitness for use and data fitness for purpose. For data fitness for use, we can say that this is general. It may be generated with respect to the purpose of improving data quality by detecting errors, their basic causes, and correcting them, as well as taking measures to prevent the errors from reoccurring. Data fitness for purpose, however, must be considered as more specific and case dependent. When we take the case of ecological niche modeling, ENM, for that data we have to use, we need to pay attention to the scientific name of species and make sure that they are univocal, that's unique, and updated You must also be sure that the adequate geographic coordinates are provided. You must check for basis of recalls so that to discard the species, for instance, uh, species or let's say occurrences that refer to introduced species. When you take, for instance, the case of completeness of data completeness analysis, it is a little more constraining than the data on ecological niche modeling because here you pay attention for a scientific name, make sure that it is unique and updated. You must also pay attention to adequate geographic coordinates, but also the complete dates of observation must be available in terms of day, month, and year. And you must also pay attention to the basis of because so that you don't have artificial, okay, information that can create bias in your analysis. So when dealing with the different objectives of data analysis,